Okay, hey folks, getting into this next learning goal. This is on some pretty advanced stuff that you typically wouldn't see until graduate school if you went that way. So I just wanted to talk about this briefly, molecular beam experiments. So this is some pretty cool stuff and is certainly an avenue for if you're interested in physical chemistry, what you might do in graduate school. So I first want to describe what a molecular beam is and how they're made, and then what their results are. So this is the basic diagram of a crossed molecular beam experiment, where we have source number one, so one molecule type, source number two, a different molecule type, and we can actually fire these in this way and create a collision at a specified area where then the products of that collision can be detected with this detector. So typically that detector could be a mass spectrometer, so no chromatography, right? Just the mass spectrometer detector. Or it could be a photodiode. I'll just write PD for if there's light given off in the process, or even some other type of spectrometer where we might be able to get a characteristic fingerprint of the molecule in this collision. So now, how do we get these molecules to fire in this, linear pathway? Well, that's done in the following. So this source one, for example, would be this entire schematic right here. So we would start with the source of our molecules, or I'll say source of reactant molecules, and that could be a primary source or a secondary source depending on what we're doing, right? If it's a primary source, that means our molecules are emitted directly. If it's a secondary source, that means we've got some precursor in there where some reaction takes place to spit out the reactants we're interested in. So if you recall, molecules have this Maxwell-Boltzmann distribution of velocities, and they move in all sorts of random directions, right? The Brownian motion. Well, if we create this pinhole and we have roughly atmospheric pressure on this side of the pinhole and vacuum on the other side of the pinhole, they will expand out as indicated by the flow. However, if we put another pinhole, this is known as a skimmer, so it actually has this geometry which will allow molecules to flow out and around, but will also allow occasionally some molecules to make it all the way through. And then we follow that up with another device called a collimator, which again, as you can see, aims to select molecules only with the trajectories going right through. Then we will create this beam of molecules. So and if we do this twice and orient them at a certain angle, right, then we will have these little soldiers going in this straight trajectory here. What's also pretty cool about these devices, these things can typically be pitched at different angles so that you can study what happens to the reaction when you collide them at different angles. So for example, here's something we might see in a cross-molecular beam experiment where we create this map of what would lead to a successful reaction or an unsuccessful reaction. So for example, in the reaction of a Cl radical reacting with Hi to displace that to an HCl plus an I radical, there is a very specific angle of attack that leads to a specific reaction. And this kind of map can be created with this device by pitching these things in and out. So as we might guess, we can really only study elementary reactions with this thing, so individual steps within a mechanism. So the type of results that we also might see are these potential energy surfaces. So this gets complicated, so let's break it down into one thing at a time. And here we're going to look at a simplified version of that reaction I just showed. An A reacting with a BC molecule. that becomes this transition state, ABC. And that transition state can either kick back out to reactants or can kick back out to products. So that's basically a generic version of the reaction I showed. So we know that we can make a potential energy surface from the BC molecule, where now this minima describes the minimized radius of that BC. And of course, there will be energy levels, vibrational energy levels within that BC molecule. We can also create a potential energy surface of the product of the AB molecule. And so, the minima will correspond to that radius. And of course, there are also vibrational energy levels within that well. So now when we put them together in this way, we can now start to think of how this A molecule will enter the potential energy surface, make its way through the transition state, and come back out as a product. Okay? So if we look on this y-axis here, RBC, and the line indicated, right, that line indicates the minimum bond energy. I know it's hard to imagine this thing, right? But this is a topography map of these two potential energy surfaces put together at this 90-degree angle, right? So this would be for this like 90-degree collision. And of course, we can imagine what that looks like if we sweep it through a whole bunch of different angles. That would be computationally challenging, but all the same possible. So here is where our RBC starts initially. And if we imagine an A molecule coming into this well, right, it's coming in through here. And now as it moves through this potential energy surface, it hits a saddle point, which we know as the transition state. So we can really think of that transition state as the top of our activation energy curve. So there's our reactants, there's our products, and zooming way into that gives us this diagram, right? So what we want to see is a reactant successfully move through the transition state and on to products. So now, once we're at this transition state here, we can begin to move through to the other side. And now you notice on the x-axis, that's RAB, and this line here indicates the equilibrium bond distance of RAB. So let's look at a couple of different trajectories, all right? So in this topography map, right here, this first trajectory we're showing is A moving through the potential energy minimas. So we can see how it crosses, this mark on this topography map, right? It is hitting the minimas. And what I want to point out here is this would be, an A colliding with a BC in its ground state, and then leaving in its ground state. And what you'll notice here is the, right, so again, this is BC on this axis and AB on this axis. So it is oscillating. It's hard to tell, but it's oscillating ever so slightly, right? It goes down and it goes back up. And then now if we look here, the AB bond is elongated ever so slightly and then compresses into its equilibrium bond distance. So now we could also imagine a scenario in which a BC molecule is in a vibrationally excited state. And in that case, it has this oscillatory nature, right? So we can imagine, right, in our potential energy surface, the ground state was down there at the bottom, near the minima, but an excited vibrational state or multiple vibrational states are higher up. So when viewed as a topography, right, this trajectory shows vibrational excitation. And of course, if something enters the transition state in a vibrationally excited way, then it could also exit the transition state in a vibrationally excited way. So there are other potentials as well. We could imagine a scenario in which a reactant comes in at a ground state, but is not in the right orientation for reaction to happen. So it just kicks right back out. So that would be an unsuccessful reaction. Okay, and these top two would be successful reactions as it's moving through the transition state. So we'll say unsuccessful for these two. And now, as you can see in this panel D, it is entering the transition state in a vibrationally excited state. However, from either the combination of it not colliding at the right angle or it being out of phase vibrationally with the product's potential energy surface, it also gets kicked back out. Okay? So this would be what we probe by changing the angle in that molecular beam experiment. And the last thing I'll end at is another possibility, which would be for chemiluminescence. And specifically here, we'll talk about infrared chemiluminescence, where a vibrationally excited molecule emits infrared radiation as it returns to the ground state. So again, when we imagine now a molecule entering this potential energy surface with this vibrational excess energy, right? If it goes into the transition state and then leaves the transition state in its ground state, some of that energy has to go somewhere. So that energy will be emitted in the form of light. And because H nu, right? And so because we're talking about vibrational states here, the type of light that would be emitted would be infrared. So one way that we could actually purposefully do this, if we wanted to purposefully promote a molecule to an exact state, we could do that with laser-induced fluorescence. So in other words, we could use a laser at a very specific wavelength to excite a molecule to a specific vibrational energy level that we want. And we could then monitor this infrared chemiluminescence as a function of the laser-induced fluorescence that we give it. So this really some complicated stuff going on that I'm describing here very briefly. So I only want you to just have some familiarity with this and be able to look at these contour profiles and kind of have a reasonable assessment of what's going on. So for example, is the molecule entering in the ground state and leaving in the ground state? Is it entering in an excited state and leaving in the ground state? Or is it entering in the excited state and leaving as an excited state? Or even is it entering this transition state and doesn't have the right angle of attack or doesn't have the right vibrational phase and then gets kicked right out back to reactants? Okay. All right, folks, I'll see you in the next video.